Chi-square test. Chi-square test helps us to decide whether the variation that we are observing is purely because of chance or is it because of some meaning embedded in the data points that we are seeing. For example, let's say you run an experiment where you have a coin and you are tossing that coin 100 times and you get 30 heads and 70 tails. Now you want to decide whether this coin is a fair coin or not. Yeah. So you can use a chi-square test for that because you have some observed data points, which is 70-30 ratio, and you have an expected ratio of 50-50, right? So over many tosses, you can expect a coin to give you roughly 50 heads and 50 tails. So chi-square test helps us understand whether the variation that we are observing is purely due to chance or there is really some embedded information that you need to act on. Yeah. So the formula for chi-square test to calculate the sample chi-squared, you look at the observed data point is to, in this case we got, let's say, 30 heads and 60 tails. Yeah. 30 heads and 70 tails, and then you expect to get 50 heads and 50 tails. So you have some observed experiment and some observed data points, and you have some expectation going in. You have some expectation that, hey, this is what the fair situation looks like. You compare your expected value with the observed value by taking the difference, observed minus expected, square it, and you divide that by expected value, and then you do it for all possible observations, and so you sum them. So you do it for heads, you do this for tails, and then you sum that for both heads and tails. Certain times let's say you have a cube, dice cube, that you want to find out whether it's fair or not. It has like 6 sides. So now this will be I from 1 to 6, because there are 6 possibilities of observations and expectations. Similarly, you could have any number of observations and expectations for your data points. So you look at what was my observed heads, 30, expected 50, and I expect 50. So 30 minus 50 squared divided by 50. And then I do the same for tails, plus 70 minus 50 divided by 50 squared. So you do that, you get your chi-squared. So this is your sample chi-squared. And once you have that, you can use your sample chi-squared and compare that with a distribution of, let's say, 1 billion standard chi-squared. So what are some of the steps? Let's go through them one by one again. So first you create a null hypothesis. In 5 steps, we can easily decide whether this is, in this case, let's say, a fair coin or not a fair coin. Yeah. So the first step is we do a null hypothesis. Step 1, we assume that the coin is fair. Yeah. So that means we have an expectation already going in that there is a 50-50% chance of heads and tails. So we have an expected probability. So step 1 is we are defining what is our expectation. So step 1, define expectation. And once you have those probabilities, write them down. Yeah. Step 2, from the expected probabilities, you find out expected outcomes. So if you are running this experiment of tossing this coin 200 times, then the expected outcome is 100 and 100. Yeah. So 100 heads, 100 tails. But if you're running it only twice, expected outcome is 1 and 1. So from the probability, based on the number of iterations you have, you find out expected outcome. So you've already solved for this part of the chi-squared equation. You first form a null hypothesis, which gives you an expectation going in. From the expectation, you find out the expected outcome or the counts. From that, you can easily look at your observed data points and calculate the chi-squared using this formula that we just discussed, which is observed minus expected upon expected, observed minus expected squared divided by expected. Sum of all of those observations, we get the chi-squared, sample chi-squared. Yeah. So this is our sample chi-squared. Yeah, so we first went in with a expected probability, we have the observed data points already, we calculated the sample chi-squared. So with these three steps, we calculated the sample chi-squared. Two more steps remain. We get a billion such standard chi-square distribution values, which we can get, and then we get that using the degrees of freedom that's appropriate. In this case, there are only two possible outcomes. So unique outcomes is 2, so degrees of freedom should be 2 minus 1, so 1. So for 1 degree of freedom, we get a large number of standard chi-square distribution values. So we get this billion samples of standard chi-square distribution, and then now we compare the p-value or the probability. How rare is my probability of getting the sample chi-squared that I got compared to a billion sample chi-squared? Yeah. So we calculate the p-value, which is nothing but the probability of observing a chi-square greater than or equal to my sample chi-square. Yeah. So if my significance level is, let's say, 5%, meaning, hey, I'm only going to make this decision if I'm at least 95% sure. So then I can calculate the p-value very easily. I can say, hey, just count from all of these billion sample chi-squared that I got, how many of them are greater than or equal to my sample observed chi-squared. So if that value is less than 5% and your significance threshold is 5%, then you'll be like, yes, this is a rare observation, meaning there's something wrong here. Yeah. So you calculate the p-value, or you can calculate the critical value, which is nothing but for a 5% significance, you do a 95 percentile of this billion data points that you got. Calculate the 95 percentile of these chi-squared. That will be your critical value. So either using the p-value or the critical value with a 5% threshold, you can make a decision. And so that's your final step, which is if you do these 5 steps, you can make a decision. If your p-value or the probability of getting sample chi-squared greater than or equal to the values in this billion distribution is greater than or equal to sample chi-squared is greater than is less than 5. If my p-value is less than 5, meaning I have an evidence against the null hypothesis, I can reject the null. Yeah, meaning it's basically saying there's only 1% chance of observing. If, let's say my p-value was 0.01. Yeah, if my p-value was 0.01, that is basically saying I have a 1% chance of observing or getting a sample chi-squared that I got. Yeah? But if p-value is less than 0.05, then we reject the null hypothesis. Yeah, so you reject the null hypothesis if your p-value is less than 0.05 or your sample chi-squared is greater than your critical value. Yeah. Either way, there's 2 ways of doing the same thing. You reject your null hypothesis if your p-value is less than 0.05, meaning this is significant. You cannot ignore this value, or you look at your sample chi-squared. If it's greater than your critical value, then you reject the null hypothesis. In this case, if you reject the null hypothesis, then you say, hey, I reject the fact that these are fair coins, meaning these 50-50 probabilities don't exist, or because they are not fair coins, or in a sense I'm saying these are not fair coins. Yeah? So you can also visualize this using a histogram. Look at all of these data points, the billion data points that you got from sample chi-square distribution, plot them, and then find out where your critical value is. Yeah? And if your sample chi-squared is greater, yeah, then your critical value, then you reject the null hypothesis. But if it's less than the critical value, then you accept the null hypothesis. And similarly, if your p-value is less than 5% significant threshold or 0.05, then you reject the null hypothesis. Yeah. Okay, so that's sample chi-squared. Start with expected, calculate based on expected probability, calculate the chi-squared. Once you calculate the chi-squared, find out how rare is this possibility of getting this p-value for this sample chi-squared and critical value, and then accept or reject based on these thresholds. Okay. Thanks.